right, worksheet 4. We're already here. That must mean if you're here, you're in week 2 already. Great. The rest of the semester is going to be basically the same. And hopefully you enjoyed the writing project. And here we start, second week. Okay, so we are going to do a little bit of trig review, but just really quick. There's a whole separate video that if you are the least bit rusty on trig, I want you to watch that. I have taught this course many times with different book, slightly different presentation. I have lots of materials and also pre-calculus I've taught and calculus 2, and so I can insert little review videos from my previous courses, so I will do that from time to time. So you will notice that if you're using the playlist, then you'll just see them come up right in the playlist as optional videos. And if you're grabbing these links directly off of Blackboard, then they'll be available there too. Okay, so if you want to find the sine or cosine of an angle, the angle I'm going to mark as theta. And I'm going to say this is the x, this is the y, and this is r, or the hypotenuse. So we have the basic trig identities: sine, cosine, tangent, and then the reciprocals: cotan, secant, cosecant. These are all thetas. And sine is y over r, cosine is x over r, tangent is sine over cosine, so it's y over x. And cotan is x over y, secant is r over x, cosecant is r over y. So think of them as kind of nested. These guys are a pair, these guys are a pair, these guys are a pair. If you're like me, your classmates and you are probably like, why is sine named sine? Why is cosine named cosine? And they're not reciprocals, but tan and cotan are reciprocals. So what's going on here? Well, the reason is co means complement. Cosine means complement, the complement's sine. Okay, that's what that means. So what it means is the cosine of theta means if you move the theta up here, then what would the sine be? That's what it's really saying. It has nothing to do with being a reciprocal. It has to do with being a complement. And so that's how that notation came to be. And so now you know the secret. It took me years to figure that out because nobody told me. Now I'm telling you. Okay, now if you now take theta or t out to 2 pi, this is like going on a circle. Okay, you're starting at here, theta is 0, and then theta is pi over 4, pi over 2, all the way up to pi over here at 180 degrees. And then 360 degrees is 0, is the same as 2 pi. So you just keep moving around the circle like that. Okay, so then you're going to ask questions about what happens to these various trig identities as you move around that unit circle. So the first thing we want to do actually is get rid of this graph and get rid of all this. I'm going to clean up this space a little bit. I like to do the following on paper with students, and so I'm going to ask you, this is actually question 2 on the worksheet, I'm going to ask you to do this with me. There's no way to test that you've done this, so there's no quiz question analog, but I want you to do this with me. This is exercise number 2 on your worksheet. So I want you to graph this as follows. I want you to make a grid. You'd think this would be easier on the computer than it is. I want you to make yourself like a grid, and better than what I just did. I'm going to straighten this out. You want to make a 4 by 2 grid. I don't care what size your squares or rectangles are. They could be squares or rectangles, it doesn't matter, but they should all be roughly the same size. Okay? I want you to draw that for yourself, and you're going to place a sine curve in there with me, and the cosine curve works just the same way. I'm going to do this very carefully. I've seen so many disgusting trig functions in my life teaching that I just started doing this for people, and the graphics got so much better. Okay, so what you're going to do is you're going to first of all sort of put these little dots here to let you know this is where your curve is going to go. You're going to go through those points. But not only do we know what the points are, so this is 2 pi. We're going to graph sine of x. I want you to remind yourself that the curve is going to be flat when the function is 1 or -1. And it's going to have essentially a 45-degree angle at the other crossings. Now, it doesn't have to be 45 degrees. If you happen to draw rectangles that are like that, then it can be like steeper. It doesn't matter. But once you pick that angle, the other angle is going to be exactly the same, but in the other direction. So your angles should be mirror images of each other. And then each one of these little pieces is going to look like so. It's going to look flat, and it's going to just come right down. It's going to dive in. That's it. If you can repeat that shape exactly each time, I mean, it doesn't have to be perfect, but you just make it dive in. Then you can turn your paper. I'm turning my computer around. Okay, then you just do flat and dive straight in. Start off flat and then level off. And the computer thought it could do a better job than me, but this is what I wanted. Okay, all right. That's how you carefully draw your sine curve. And the other thing I started doing after like failing several times is to tell the students, when you're told to graph a sine function, just draw yourself a sine function, because the first thing you want to do is just do this. It's either going to be a sine or cosine. The cosine is the same, but you start here instead, and then you have one more segment over there. Okay? But you just draw yourself, if you're drawing a sine curve or cosine or minus cosine or minus sine, once you know what the template should look like, draw it out, and then worry about putting in all the decorations. I call them decorations. So let's say what we really wanted to do is 4 times 3 plus 4 times sine of pi x. Maybe that's what I was planning on graphing. They all look the same. So why don't you just change the axis after the fact? I mean, that's what MATLAB does, and it's really expensive software. So why don't you just make your graph and then put the labels on? So for example, my midpoint is my horizontal, I guess, average is going to be 3. If I add 4, it's going to be 7. If I subtract 4, it's going to be -1. What else do I need to know? I need to know something. So by the way, some language here. This thing is called 4 is equal to 7 minus 3, and it's also the amplitude. The amplitude is half of the whole domain, essentially. So that's the amplitude. And then this is getting to this idea of frequency or period. You want to know when this guy is going to get to 2 pi. And in this case, x equals 2 is going to be the period. Period is 2. Okay? And the frequency, otherwise known as the wavelength, is just going to be, hold on a second. The frequency is just going to be the reciprocal of your period. So you just take the reciprocal. Okay? All right. So let's just go ahead and finish labeling this. And so if the exercise said plot 1 period of this function, then just do what it says. Plot 1 period of this function, and then stick the labels on after the fact. I see too many people like saying, oh, okay, I'm going to go from 1 to -1, and then they're like, wait, I need to adjust that. I need to put it up there, and then they're erasing. It's like, forget that. Forget that. Just pretend like you're a computer. Do what it says. Plot the sine function. Just stick the labels on after the fact. And then you can kind of back off and say, if the question said, give all the axes, then you can say, fine, put the axis back in here. There we go. There's your axis. You wanted it so badly. Here's your other axis. It's still here. Sometimes that other axis moves. It depends if we had a shift. Okay, so sometimes, let me just adjust this problem slightly. I'm going to change these guys around. I'm going to move the other axis. Okay, I'm not going to mess with the period or the frequency, but I'm going to still mess with this a little bit. I'm just going to give myself more room to write. If I said like -0.2, all right, then I have a problem because I've messed everything up, right? No, I haven't messed anything up. I say pi x minus 0.2 equals 2 pi, and I still solve for x. It just looks messy. It's going to be 2 pi plus 0.2 over pi. X is going to be 2 plus 0.2 over pi, but who cares? I mean, that's what this thing is. So this is just going to be, here is going to be 2 plus 0.2 over pi, and you can calculate that on your calculator, but that's where it is. Who cares? That's where it happens to be. Over here, this is going to be 1 plus 0.2 over pi, and this is just going to be 0.2 over pi, right? So who cares? That's just where it is. If somebody's so hung up about your axis being off, then you just say, fine, here's my new axis. There you go. Are you happy? You should be happy because I gave you that axis you so desperately wanted. There you go. There's your axis, both of them. And then I'm just going to extend this curve a little bit. There we go. There you go. And then if they want to know where 2 pi is, you say, well, it's roughly over here. Okay, there we go. Then nobody can be unhappy with you. Okay, so that's what I think about graphing. It's lots of fun to graph the tan, cotan, secant, cosecant, but I'm not going to do that right now. We're only focusing on sine and cosine in this lesson. Okay, but we do want to focus on what happens if somebody gives you a plot and then they expect you to figure out what's going on. So there, that's a sine curve of some sort. Luckily, we start at 0. And we're going to end at, where are we going to end? I don't know. Let me end somewhere. 17. Okay, and then I need some kind of max, min. Maybe this is 25 and this is 15. So I ask you to write me a function, write me what this is. And then I say, okay, well, the amplitude is half of this distance. So the distance between 25 and 15 is 10. So the amplitude is clearly 5. And so 10 is this halfway point. So that's the middle of that function. Now, what is the period? Well, I would like to know how I'm going to make the period. So I should end up with, I'm going to do sine of something. Sine of some kind of theta is, and I'm going to need at t equals 17, I want theta to equal to 2 pi. So I'm not afraid of wasting variables. I'm just going to actually say this is theta equals 2 pi, and I just have to figure out what t is. T is running along at a different time speed. Well, who cares? Theta is 2 pi when t is 17, but I can go ahead and start constructing this function before I actually know what's going on. So this function is 5 sine of theta, but it's 10 plus 5 times sine of theta. So I'm halfway there. And now I just need to figure out how to mess with this so that so I'm going to convert to t's instead of using theta. So it's going to be 10 plus 5 sine of something here, right? I'm going to put t in. T is going to be 17. How can I make sure that if I let t equal 17, then this expression has to be 2 pi. How will I do that? Okay, so remember, t is going to be 17 at some point when you want to make sure that this expression is going to be 2 pi. So I'm going to have to divide by 17 and multiply by 2 pi. Now that fraction may end up having a form that's simpler, but you can just, right now 17 is kind of a pain. We just make sure that works. If I let t equal 17, does that whole theta mess turn into 2 pi? It sure does. And so I've figured out what I want this thing to do. Now, I haven't told you what to do if the function is shifted, so let me do one of those. Okay, for the sake of argument, let's not worry about all the other kind of shifting that might be going on. Let's assume that this is right where we expect it to be at -1 to 1, and the only extra thing we have to worry about, the only thing we're now really worried about is the fact that we're offset, and maybe 2 pi is really over here, and we want to know how much we're offset by, and we can use essentially the same techniques. You can just draw your curve and figure out what happens after the fact. So what is this? Let's make this 1/2. Okay, we can mix and match the pi's and the non-pi's. So what we're doing is we're doing some kind of shift. We're saying sine of, well, is this function early or late? This function is early. So it's x plus 1/2. So it's doing a look ahead. All right, so you actually know that from the last unit, but I just wanted to kind of bring that in again. So that's how you figure out what's going on with that. And finally, just a little bit, how do we do composite functions with trig? It's really like composite functions without trig. So if I had, I'm not using tangent today, so I'm going to go ahead and use it just to be funny. If I have tan x and I want to raise it to the power of 6, I could say f of x is x to the 6th and g of x is tan of x, and this whole thing is f of g of x. And you could get creative with that. You could say, wait, what if I want to put like the square here? You can, and then you would have to cube that. So you could do that kind of thing too. So that's just kind of cute. One thing I do want to do, I forgot to do, so I'm going to do it now. It's out of sequence, but I don't care. Okay, I wanted to show you what happens if you look at sine of x squared. So this is what sine looks like, right? You're just going to go ding, ding, ding. But if you square it, you're going to actually get a function that looks like this. And that makes sense. Because why? Because zeros are going to be zeros, ones are going to be ones, and negative ones are going to turn into ones as well. So what you've got yourself here is you've actually got yourself a shifted curve, right? And so what you had originally, you had sine of x squared. You've now turned this into a minus cosine of 2x, but you've divided it by 2 and then lifted it so that it's lifted by a half, right? Because if you divided it by 2 and then lifted it by a half, this is where you'd end up. And so you've actually just demonstrated, if you believe that by squaring sine you still get a sine or cosine curve back, you've just proven this identity that maybe you've had trouble memorizing in the past. I really don't like memorizing that. So I just always just graph it and say, what happens when I square sine? This is what happens. What happens when I square cosine? Well, I end up with this kind of thing. Ding, ding, ding. Same thing again. Right? And I end up with the same kind of argument. And I'm like, well, that's basically like, you know, you trace out the logic and you get the other identity. So that's a cool trick I wanted to show you. Now find out I probably did it wrong, but even if I did it wrong, you got to double check what I just did. Let me just double check what I just did. Not that I just trust any old thing I pick up on the internet, but it looks like we did it right. We said minus cosine of 2x and then we added a half, so that looks right. Oh yeah, and just in your homework, no fair if you say like f of g of x is equal to whatever. It's not a composite function if you just put all the action in g and let f be f equals y equals x. It's also no fair if g of x is g equals x. That's just completely defeating the purpose of having a composite function exercise. So you're not allowed to use the identity function y equals x when you're building these composite functions, just because it just takes all the fun out of the exercise. And one last fun fact I wanted to tell you for the day is that if you have something like sine, any multiple times sine of x plus any other multiple times cosine of x, clearly the period's still going to be 2 pi because they're both running off of x's. But what you may not have known is you can rewrite it as sine some c, whatever the c ends up being. I don't know how to compute it because it depends on the function. Depends on a and b. But it's going to be x plus some kind of shift, plus or minus some kind of shift, or some other, actually it's going to be the same c, cosine x plus like a different shift. Okay, so you can rewrite the sum of any sine and cosines even after you scale them. Okay, you can try to take sine and cosine and scale them and add them together, you're still going to get a function of the same period, but weirder than that, it's just another sine or cosine curve, which is really freaky. That means you can take these guys and combine them somehow into a grand new max value, and then just try to figure out what the shift in the angle is. Really cool stuff. Okay, so I think that's all you need for worksheet 4. And I will insert in the playlist review videos and examples and things like that.